So here we're going to welcome Brian Katz. He's going to talk to us about Inquiring Minds Want to Know Part 2.
Thank you. Thank you all for being here as the conference comes to an end. So what we're going to do today is we're going to talk a little about the point of this session. We're going to do some synthesis work and some sharing. So it's much like the last round, but sort of at a different target. So in the first round, we did a little mathematics. We explored a mathematical phenomenon, and we were reflective about the sort of general mathematical moves, the sort of actions a mathematician undertakes as we were doing that. And so we tried to bring those moves to the surface and give them names so that we could articulate them. So we tried to become consciously aware of what it is we're doing when we're exploring a mathematical phenomenon. The goal for this round is to organize all of that raw data into something that's a little bit more coherent, and one of the goals is to produce something akin to the scientific method, something that maybe has a moniker and has a little picture that's really easy to remember, something that you could give to a student to help them understand the big picture. Because right now, I suspect in your classes you say, like, oh yeah, it's good when you do this kind of thing, but I'm not sure that they get the big picture, because it's really hard. So a couple of examples of what we're aiming for each group. So this is, in fact, a picture of the scientific method, and you can see how there's some loops in it having to do with whether or not the data sort of aligns with the hypothesis, and it sort of loops back around and it gives you new questions to ask, and the whole process starts back over again. It's meant more as sort of this is what it might look like rather than the details of this one. Another example that's sadly less colorful, this one comes from social science. This one's about the interaction between qualitative and quantitative data in social science. So there's some, you can't see my mouse. There's some traditional quantitative data analysis where maybe you have a survey and it has numerical values and you work with that. But eventually you realize that there can sometimes be, like, maybe if you split your population into two groups, that explains some weirdness in your data. And then you start to say, okay, the lived experience of those two groups is different. Let's go do some qualitative work with them to sort of understand that, and that gives us new focused things. And once we have a really focused question, then we can ask something quantitative again. So it is also cyclic. Not that you have to be cyclic, but this is another example of what this might end up looking like. So we have three sources of raw data. One is up on the wall from the previous session. These are articulated mathematical moves that each table mentioned. You are all, in some ways, mathematicians, so you all have experience doing mathematics for fun/research. I didn't put an "and" there because that implies that research isn't fun. And then most of you, I suspect, or all of you, are in the classroom with students, and you have seen them do productive mathematical behaviors that you have encouraged, and so you have experience of seeing other people do mathematics. So your assignment is, in your small groups, with a fresh sheet of paper and your multiple colors of markers, to produce an organized version of the process of doing mathematics, akin to the two examples we did before. So I suspect you're going to want to chat, brainstorm about the structure, think about what's important, what you're trying to encode, and then as our time goes on, start drawing together. So we'll come pass out fresh blank pieces of paper in just a minute. So thank you. Very good work today. We clearly do not have time to talk about all of these, but I want to make sure we talk about at least a couple. And this group volunteered, by saying they were done a minute and a half ago, they volunteered to go first. So they need the microphone. They need somebody to hold, perhaps somebody to play Vanna White, somebody to talk.
I went first just so I could remind everyone to use the microphone.
All
right, so first of all, I'm Dana Ernst. Thank you. Earth. So first of all, I figured out why no one's done this before. Because it's really hard.
Yes.
And that's
excellent observation.
Yeah.
Thank you.
So I think the idea here is that this is really complicated because there's so many things going on at once. So that's not completely drawn. It's supposed to be a complete graph on 10 vertices.
You just move that way.
So I'll tell you what the vertices are on there, and then we'll just talk about what's going on here. And I'll make this quick because I know other people want to go. So we have formulating questions, observation, prioritizing, testing conjectures, conjecturing, concluding, informal argumentation, formalizing, and proof. And then we have an arrow called generalization, sort of feeding back into the loop. So a lot of these things we sort of thought were things that were just all of us don't all start in the same spot, and we bounce around, and it's sort of like this static cloud of electrons floating, and then towards the bottom there kind of is a flow, but then bounces you back into the cloud, but that's kind of what we were trying to capture there.
Great. So one of the groups over here wanted, Sue in particular, wanted a visual metaphor that sort of the first impression had a big part of the idea, and you're saying that sort of it's erratic at first, it funnels, and then it sort of cycles back. So there's a lot of detail to look more deeply, but that sort of big idea about the process is encoded. Yeah. Great. So maybe we'll talk a little bit more about them in contrast. So you guys use technology. Let's see if we can make this work. So about 5.
Okay, I'm Perry Ford from the University of Nebraska at Kearney, and we were talking about how flowcharts kind of give the idea to students that they are supposed to, or well, maybe that there is a step-by-step process of going through, and as mathematicians, that might be something that we're like, no, there's not a step-by-step process. So that complete graph idea was something that we talked about, and I was thinking, just pull out an idea out of your toolbox and different ideas. But then Sue talked about that for our own students, and as we are teaching our students, having that flowchart is helpful to them so that they know what to address, something to try, where to start, giving them a starting point.
Now we have.
So this is a spiral, and we are going with upper, and it is inspired by Polya's problem-solving strategies. We have understand, play, plan, execute, and revisit. By execute, we are not killing anything, and so if you have a better synonym for execute, that'd be great. But it's a spiral because we're going to keep doing this process until we get to some sort of conclusion or solution, and then it just keeps going on forever and ever. And from the 5 elements of effective thinking, we have this flow, past, present, future. This is an infinite spiral. It's going to keep going down and down.
Excellent. Thank you. Shall we clap for our team so far? We have an IT professional here, so.
Cindy York from Northern Illinois University. So I was a little more linear in my thinking, and as my group was talking, I was trying to throw up onto the computer what they were talking about. So it's more of a flow chart than anything of how to problem solve. I'm going to let one of them talk about it, though.
Okay, I'm Bob. So we threw out all these ideas, and then she threw them on the paper instantly. So I think we're not wildly different from the other groups. We did have a few pieces of sort of the what ifs and try other things. And then I liked the execute because we talked briefly about sort of executive function on top of your problem solving, sort of where are you in the chart, and are you making progress, or should you abandon the current strategy? And we couldn't quite put that in the chart in a good place, so the spiral maybe works better for that. So
excellent, thank you. Should we clap? Yeah. So in our last minute, thank you. As Dana pointed out, this is very hard, something you probably want to spend a lot more time than just half an hour in this one session. So I have spent some time thinking about this, and I'm not going to say that this one's perfect, but here's the best one I've made so far. It says unintentionally blank slide, so I don't destroy the secret by accident earlier. So it's cyclic. It's very cyclical. Everything is made of circles in here, so everything's very round. So there's sort of 3 main objects. There's questions, definitions, and theorems, and the moves are sort of to move between them. So to go from a question to a definition is abstraction. That's sort of clarifying the rules from before. Within definitions, you explore a lot of the example work I was hearing about. To go from definitions to theorems, there's sort of this investigation and conjecture, sort of organizing work. Inside theorems, there's justification, which is where the proof comes in. Application, so you return to your original question and you take what you learned and see if it says anything about it, or maybe it doesn't. And when you get back there, now you know more than you did before, and you can ask new questions, which allows you to produce new questions and start the whole cycle over again. So this is sort of a version that I've produced. What the next slide is not a shameful plug, it's a shameless plug, because, as Starboard points out, because I really believe that this idea is important, and I've thought about it, and so I want to share it. And so that image I just produced is basically encoded in the structure of particularly the graphs chapter of this book, but all of our books. This is the inquiry-based textbook that Starboard and I wrote. And so we really tried to put all this meta content in there, and each chapter ends with a discussion of the inquiry moves that we think we asked you to use in that chapter. And so as Elizabeth did as well at the end, hopefully now you have a little bit clearer idea of what it is we're looking for in this contributed paper session in January. This is really hard work, so if you've done some of this hard work successfully, or if you've engaged students with this work, or if you've produced something that helps your students understand this work, we want to hear what you're doing to help to bring inquiry to the surface, make it a coherent and clear picture. So that is our session. Thank you.
Sandra Larson, University of Colorado Boulder. I think it's really very, very useful for students to have chances to identify the general behaviors amidst the thicket of specifics that we have them mired in any course. And I would argue that you could do a simpler version of this with students that would be very helpful, which is to identify what kinds of strategies have helped us solve problems in this class so far. Make a list, and then visit it again in a few weeks, and add to the list, and say, can we give examples of when we've used these? And just keep using that terminology, and it can be self-invented, it could be the Dana strategy, which is whatever Dana did on Thursday last week. That could be part of the classroom language, but I think it's really useful to do this with students. And it wouldn't have to go as far as this to try to get the sequencing and so on, but just the list of tactics. So, good stuff.
Yes, metacognition sort of writ large is very close to this. Sarah Marie has it.
Sarah Marie Belcastro, and I just wanted to share something that happened right after Dana held up their sheet. So Bill looked at it and said, oh, it's like a Klein bottle. And then Sue said, it is, because when you come back around, you're looking at things from a different perspective. And then I was like, wait, I bet I could draw that without edges on a Klein bottle. And then I remembered you said it was supposed to be K10, which doesn't embed on the Klein bottle, but if you can get rid of some edges, I will embed that on the Klein bottle and make a great drawing for you.
Excellent. So if you're curious what some of the things I've done with my students to try to help with this, one thing is that it's hard for them to see what they're doing while they're learning the new content. So I teach a sophomore course that comes after a discrete math class where they learn a little graph theory, and I actually have them read an inquiry-based text, the chapter about graphs, and reflect on basically what we did in the first session. What are the moves that are being made? And then we go through a version of this activity together, but it's content they're very familiar with. They spent a month or more on a previous term thinking about that. They've read something. And so we do this work together. And if that's why I know Dana had seen that picture before, because that's what I talked about at MathFest last year. And you can find that talk on YouTube. I think it's a bridge from IBL to student inquiry. So.
Can you flick back 2 slides to your picture?
Yes.
I had one comment I wanted to make. Yeah, that. So I think like in our proof-based classes, and this is different in other classes, we spend so much time assessing students over here, right? And this is fun, right? But I think like when we fall in love with mathematics and the joy that we got out of it, it's like this whole process, but we spend so much time focusing on assessing students over here. So that was really powerful for me to suddenly, I mean, I knew it, but I was suddenly deeply reflecting on that. So I appreciate that happened for me, so thank you.
In many ways, the thing that I think makes people notice that I'm a mathematician is the abstraction. I'm like, okay, so what exactly are we talking about right now? So what is that? Like figuring out exactly what the rules are, the way I interact with language. And so I totally agree, we spend all our time on the justification, but that's the thing that makes us different. Right. And of course, there's the joy, right. Yes. Yeah, Sue has a last comment, I think.
You can all, no, you can't leave yet. So I was going to ask you, Brian, but Dana, you can answer if you want. So my experience teaching tends to be that students pay attention to what they're assessed on. So how do you assess the other loops here? What are some of the ways that you assess abstraction, exploration, extension, conjecture, et cetera? Like Dana was saying, I think we have a lot of focus on how we assess student learning of justification. So I don't mean necessarily a test, but how do you determine that students have learned these things? I'm sure you've thought about this.
Wiki assignments probably. Oh, yeah. Do you want to take it?
If you like, yeah.
I can just talk in this one. Well, one of the things that I do, I need to direct your question to Brian, but he's still thinking. One thing I do is I try to make room for like Dana was pointing out, there's this part that we sort of don't make room for in our classes. So I use a wiki in my class, and my students make conjectures. It's part of what they can do for their homework. And then they also refine those conjectures. So it's actually an assignment to do that work. And I'm not evaluating them on whether the conjectures are correct, because they never are at first. But the work is part of what they can do for their homework.
So I'm going to have to think about this for another 30 years or so, but I think the answer that I give is sort of in the category of the hard answer, which is changing how my students are spending their time. If I want to evaluate things and I value these things, then they have to be doing them, as opposed to trying to find a way to evaluate it amid me doing sort of what I may have done before. So I teach a course that doesn't, where they do the class where they develop this. Their final project is evaluated based on how well they ask new questions of their own. So we just made 2 credits in our major to have space for that, and then in my other courses, cut some other things out to make time for it, which is a really hard answer. And I agree, I'll have to think about it forever. But I think we're out of time. Thank you.